Okay, let's give a detailed example of how to work a convolution problem using the mathematical definition. So big picture, remember that convolution is how to directly compute the output if we're given an input and an impulse response. And we represent this using the notation that the output is equal to the input convolved with the impulse response. The mathematical definition of convolution is the integral. We have to use a dummy variable of tau of our input x of tau times h of t minus tau d tau. So tau is a dummy variable, it will go away, and we'll be left with just a function of t. So let me give a detailed example. Say we have an input that decays. And it's 0 up until t equals 2. And at 2, it pops up to a value of 2. Here's the 2 out here. And it decays down. Decays down relatively quickly. It's negative. Its time constant is 1 over this coefficient is 1/3. So after about time constants, 5 time constants, or roughly 1.5 seconds, it's decayed to about 99% of its final value. So this will decay down to about 1% of 2, or about 0.02 after 5 time constants, which would be 5 over 3, about 1.5 seconds. Our impulse response, let's say it looks like a delayed step. Then we can set up our answer. We can find our output is the integral from negative infinity to infinity of x of tau times h of t minus tau d tau. That'll be the integral of x of tau. Well, if x of t is this, then x of tau is the exact same. Just every time we see a t, we'll replace it with tau. And we'll multiply it by our h of t. Now this says that every time we see a t in our impulse function, we will replace it with a t minus tau. So that would be u of replacing t with t minus tau, and then minus 1, all d tau. So this is where we're going to use what I call Square's rule, that says if you've got an integral that's got complicated looking step or impulses to it, get rid of those steps and impulses first by changing around these limits of the integral, and then do the integration once you've got the simplified limits. So we've got this step, and we've got this step. And so I'm firstly going to graph what each of them look like, and then what their product looks like, and that will tell me how to change these limits. So let me draw the first part of the step. The first part is u of tau minus 2. So I know that it goes to, something changes in the step when the argument is 0, and the argument is 0 when tau is 2. So when it's 2, something is changing. That's when the argument to the step function is 0. And if my tau is very large, the argument is positive. So the step is 1. And if tau is very negative, then the argument to my step function will be negative. And so u of a negative number is 0. So that gives me the first part. Let's graph the second part. Now the second part is a function not only of tau, but also of t. So we're going to have to decide some value of t to graph this for. I'll I'm going to throw out a simple value of t that kind of makes sense to me. Let's graph it for t equals 0. And we might have to modify that depending upon what we get. When t is 0, we end up getting u of 0 minus tau minus 1 that we want to graph. So we can see that that changes. It's a step that changes when the argument is 0. So it changes at -1. For very large positive values of tau, this argument becomes negative. So u of a negative number is 0. And for very negative values of tau, the argument becomes positive, and the step function of a positive number is 1. So it looks like this. And although it does look like this, I think we could see that if we graphed it for a different number, let's say we graphed it for t equals 1, it would instead be shifted to the right by 1. And if we graphed it for t equals 2, it would be shifted to the right by 2. So in general, for any number at all, for any value of t at all, this u of t minus tau minus 1, it looks like a step that drops down at t minus 1. And again, you could see that by asking yourself, for what value is this argument 0? For what values of tau is t minus tau minus 1 equal to 0? Because that's when it will, of course, when the argument of the step is 0, that's when it does its thing. And we're interested in what value of tau, since that's our independent variable, and we can solve by pulling tau out to the right, and that's equal to tau equals t minus 1. So that's where it changes. So I'm going to erase this intermediate step and realize that in general, for any time t, this is what the second part of our integral equation looks like. So now the question is, what does it look like when we multiply them together? Well, as I've graphed it, you can see that one of two things are going to happen, and it depends where it falls down. If it falls down to the left of where this goes up, we're going to get nothing. So we're going to have one of two options with this. Either we're going to get no overlap, and we'll get no overlap when this is less than this. So whenever t minus 1 is less than 2, we're not going to get any overlap. And it's just a kind of a weird way of saying we can simplify that. If t is less than 3, we'll get no overlap. So if we get no overlap, such as is shown for this particular example, there's no overlap, we'll end up getting zeros everywhere when we multiply the first equation by the second equation. When we multiply this portion by this portion, then we will get no overlap in our u of tau minus 2 times u of t minus tau minus 1. There'll be no overlap, and our integral, when we get that, will of course be 0. Another way of just thinking about it is that if t is less than 0, this first step times the second step will give you 0 everywhere for all tau. But for t greater than 3, you do get overlap. For t greater than 3, this will be to the right of this. And when you multiply these things through, you'll see you get 0 up until the time that this pops up. So it's got to be 0 in this region because you're going to be multiplying this top by this bottom. And if this is 0 for time less than 2, the product has to be 0 for time less than 2. After that, this is 1, but this is going to drop down at some point, and it will drop down at t minus 1. And for t greater than 3, this right side will be to the right of the 2, and we'll get some sort of box. And it will be of height, since, what height will it be? This is a step, this is a height of 1. And this is a step, it has a height of 1. So 1 times 1 will give this a height of 1. It's 0 out here. And its width will be t minus 1 minus 2. It'll be the right side minus the left side. So it'll have a width of t minus 1 minus 2, which again is a complicated way of just simply saying t minus 3. So now the last step is, or rather the next step, is that it means that this integral is one of two things. It's going to be either the integral of 2e to the minus 3 tau times 0 d tau for any values of t less than 3. Since for values of t less than 3, these two things are equal to 0 everywhere. That's this 0. Or it's equal to this, 2e to the minus 3 tau times this. So this is defined over 3 different places. We'd have to integrate this from negative infinity to where this begins at 2 times 0 d tau plus the integral of 2 to t minus 1 of 2e to the minus 3 tau d tau times 1 in this region plus 2e to the minus 3 tau times 0 d tau in the region of t minus 1 to infinity. So that picks up all the parts. But we know that the integral of anything times 0 is just 0. And so now we've got something much simpler. We've got an integral that is either going to be the bottom between 2 and t minus 1 of 2e to the minus 3 tau d tau, which is true for t greater than 3, or it's going to be the integral of 0, which is just 0 for t strictly less than 3. And it doesn't matter where we put our equal sign, because at exactly 3, we can consider it either all 0 here, which will be multiplying our integral by 0, so our answer is 0, or it'll be a top hat of height 1 and width 0, and if you multiply 1 by 0, it's also an area of 0. So we can put our equal sign either side, and we'll be correct. So now we can do our integral. The 2 comes out. This is negative 1/3 e to the minus 3 tau, and we're going to evaluate that between 2 and t minus 1, or it's going to be 0 if t is less than 3. So it's equal to this first integral for t greater than 3, or the second integral for t less than 3. So this is going to be minus 2/3. The second part evaluates to e to the minus 3 t minus 1 minus e to the minus 3 times 2 or 0 if t is less than 3. So I'm going to clear off the right side and continue this on. So this is equal to minus 2/3. Now just some basic algebra. We've got e to the minus 3t plus 3 minus e to the minus 6. And that's true for t greater than or equal to 3. Or it's equal to 0 for t less than 3. See, I can get rid of that minus sign by flipping the order here. Not much I can do algebraically to simplify it beyond that. But what I can do is change this to a single equation. I can say, what can I multiply this by so that it doesn't change this at all if t is greater than 3, but it multiplies this by a 0, making the whole thing 0 if t is less than 3. And the answer is a step like this. So for t greater than 3, this becomes times 1, and we get the bottom. And for t less than 3, we're multiplying it by 0, and we get the top. So this is our answer using calculus.